Hi everyone, and welcome to this tutorial bite for Oxygen Not Included, which is a comprehensive guide to cooling. This is a really important topic and is critical for progressing through the mid and late game phases. It's often the case that cooling is the last major challenge for players surviving as they learn the game, and it's certainly common to see bases die to heat once food and oxygen have been sorted. I'm going to cover what I consider to be the main ways of cooling, these being ice temp shift plates, wheeze warts, anti-entropy thermonullifiers, and thermo-aquatuner and steam turbine combos. But before going straight into those, I wanted to touch on some other methods for completeness. Firstly, a simple way to cool is to dump heat into a material and then delete it, for example by venting it to space. Whilst this is possible, the lowest temperature you can achieve is the material's input temperature, and this method is resource intensive, so I wouldn't recommend it. The next way is building a cooling loop through a frozen biome, which can cool things down for a limited time. This is done by forming a closed loop, usually with polluted water as a coolant, to move heat into the frozen biome, although this will eventually get hot. Cool slush geysers and cool salt slush geysers can also be used directly for cooling, as they produce polluted water and salt water at minus 10 degrees Celsius. I personally prefer the aquatuner and steam turbine combo as I find it more convenient, and these cooling sources can be difficult to control if you choose to use them. Another way of cooling is to use the Ice Maker and Ice E-Fan, but these two buildings are simply not very efficient in terms of power or dupe time. Very little heat is deleted when making the ice, and most of it is output into the surroundings. To use ice for cooling, I find temp shift plates much quicker, and I'll move on to that now. So this method uses ice to temporarily cool key areas. As I've just mentioned, the Ice Maker is very inefficient, so for this method I would highly recommend using ice from a frozen biome, assuming you have access to one. The following two methods of wheeze warts and anti-entropy thermonullifiers are also only found in frozen biomes as well, so it's really important to explore the map and explore early. I discussed this topic with a few tips in the tutorial bite for exploring and map movement. Assuming you have at least 800 kilograms of ice, you can use this to cool an area. I'm showing here a common example of an overheating farm, and as you can see the temperatures have gone past the plant's 30-degree temperature limit. To cool this, firstly I'm going to build a tile on the left side of the farm area, which will trap the melting ice, letting it cool the plants for longer. Then all you have to do is build a temp shift plate found under utilities and choose ice as the material. Of course you'll have to have researched these, and you can also use polluted or brine ice here too. I'm going to put it directly above the plants as it will quickly melt in this location. You can put it higher and it will still cool, but it will take longer to melt. And as you can see, the ice has temporarily overcooled the plants, but will quickly stabilise. All we do now is wait for the water temperature to reach the room temperature, and later on we can mop it up when it's equalised. Only one temp shift plate has some serious cooling power, but this is only a temporary or one-off fix. For more permanent cooling, let's look at the next three methods. And that brings me on to wheeze warts, which are a plant that will cool gases around them. As a fun bit of trivia, if you read their database entry, they're actually animals, not plants, but they behave as a plant in the game. They are found wild in frozen biomes, or in radioactive biomes in the Spaced Out DLC, and do not reproduce. Wheeze warts draw in gas on their bottom tile and output it on their top tile, cooling by 5 degrees of temperature. Note that domestic plants are 4 times more powerful than wild ones, and domestic wheeze warts move 1 kilogram of gas and require phosphorite as a fertiliser. Phosphorite can be easily found in forest or caustic biomes, or made sustainably as Draco waste. There are a couple of key points for wheeze warts, and the first is the type of gas you put them in. Because they remove 5 degrees of temperature, the heat energy deleted is then proportional to the specific heat capacity. If you aren't familiar with specific heat capacity, then check out my tutorial bite on this topic. This means they work most effectively in hydrogen, and so are commonly used in hydrogen atmospheres to maximise their impact, but you can spread these out in oxygen and they will still help to actively cool. The second key point is radiation, and this is unique to the Spaced Out DLC. Wheeze warts actually produce quite a high amount of radiation, and are a hazard to dupes especially when grouped. This makes them useful for early radbolt generation, which I'll also explain in another tutorial bite, but care must be taken when using these for cooling in the Spaced Out DLC. The next method of cooling is the anti-entropy thermonullifier, which are also found in the frozen biomes. They need to be dug out and are gravitas buildings that consume hydrogen and then cool their surroundings. These can go down to minus 173 degrees Celsius, which is extremely cold, and they are fairly powerful being the equivalent of a little under 7 Wieswatts in hydrogen. I'm showing here an example of how you might use this, including some automation control. I have a polluted water cooling line running around with radiant pipes that is cooling a hot area. To control the temperatures, in this example there's a thermopipe sensor which is linked to a gas shutoff. This turns off the hydrogen supply when the target coolant temperature is reached. I must admit though, I personally don't use anti-entropy thermonullifiers because they aren't as powerful or as easy to control as the final method to cover, the thermo-aquatuner and steam turbine combo. And moving straight onto this, here is a full working system. It is critical to understand these to really get into advanced designs, and this application has many uses. I'm not going to start here, but we'll begin with a more simple system and add the elements one at a time so it's clear what each one does. There will be reference images included at the end if you want to replicate these in your games. Before I start though, I want to touch on thermo-aquatuners versus thermoregulators, just to be clear on why the aquatuners are better. And there are 4 main reasons. 1. They are inherently twice as power efficient as the thermoregulators, even with the same coolant. 2. Liquid pipes carry 10 kg per second and gas pipes carry only 1 kg per second, meaning you'll need many more regulators to match one aquatuner. 3. Aquatuners can be fully submerged, which makes using them much easier. And 4. Common liquid coolants have a higher specific heat capacity than gas coolants. So to start here with the basics, we have a thermo-aquatuner in a steam room with a steam turbine above. The aquatuner building simply moves heat out of the coolant and into its surroundings, and the material choice is important. Overheating is an issue, and although it is possible to use gold amalgam, which gives an overheat temperature of 175 degrees Celsius, steel is highly recommended as it's much more reliable. You'll need 1200 kilograms of steel to build one aquatuner. The steam turbine needs 200 kilograms of plastic, so these are the 2 critical mid-game resources. I explained how to make these in their own tutorial bite, so check that out for more information. In this basic setup, there are 2 liquid pipe circuits. The first is the coolant, and the second is the steam turbine water output. Coolant choice is very important because the thermo-aquatuner removes a fixed 14 degrees of temperature, and this is related to the heat energy by the specific heat capacity. It's also important to ensure that only 10 kg packets are used, as the power consumed is still the same for smaller packets, but less heat energy is removed. If you want to understand specific heat capacity better, then I have a tutorial bite on this topic. The key here is to choose the coolant with a high specific heat capacity that also remains a liquid in the temperature range you need to deal with. Supercoolant is the best, but only available in the late game. So polluted water is a common choice, as its specific heat capacity is still high and has a better temperature range than other types of water. It evaporates at 120 degrees Celsius and freezes at -20. Currently, our coolant is coming in one side and going out the other, so the first change is to form a closed loop. I covered this in the tutorial bite for pipes, but I'll recap this here. A closed loop is formed as long as there's a directional building somewhere in the loop, usually a bridge. Note that here it's not strictly necessary, as the aquatuner also has an input and output, but you'll likely want to include bridges anyway to navigate your cooling loop around the base. The best way to fill the loop is to bridge on, as this prevents the loop from getting clogged. However, this can be fixed by removing liquid with the pipe emptying command, or deleting some pipe segments with liquid in and rebuilding them. Use insulated pipes made from igneous rock inside the steam room and in areas you don't wish to cool. And for areas you do want to cool, change to either granite normal pipes or radiant pipes. Although radiant pipes are clearly much more conductive, granite is usually much easier to get hold of in large quantities and is very suitable for base or farm cooling. You can also use small sections of radiant pipes, as I'm showing here, to add extra transfer in critical areas, such as hot oxygen lines from a SPOM or uninsulated base entrances. In temperature critical applications, radiant pipes become a necessity, so choose carefully. Another point to mention on the cooling loop is how to cool in space exposed areas, as there is no heat transfer in a vacuum. To counteract this, you need to use a thin layer of liquid backed by drywall to enable the heat transfer, and this can be done easily with a bottle emptier. Then the cooling loop will conduct as normal through the small layer of liquid. Going back to the build, we now have a closed loop. The last version had no temperature control. So unless there was enough heat being added to the coolant loop, eventually the coolant loop would have gotten too cold and potentially frozen. To control temperature then, a pipe thermosensor is added immediately before the aquatuner input. This is linked directly to the aquatuner with automation wire. Beware using lead for either the sensor or the wire, as it is possible for these to melt. But you don't need to use steel as they don't overheat. Now, the sensor will turn off the aquatuner if the coolant is already cold enough. But that means if the aquatuner is disabled, the liquid still needs to keep moving. Therefore, we need to add this bypass which continues through the aquatuner input and then bridges back onto the output line. The bridge is important because if it isn't included, then the pipe directions will get confused. As for what temperature to set the sensor to, this current system is a little imprecise. I'll cover how to do precise temperature cooling shortly, but for now the issue is that the aquatuner cools by 14 degrees in one go. What this means is that the coolant temperature has a 14 degrees temperature range, so you want to set your pipe thermosensor to above 7 degrees over your target temperature. To help illustrate this point, I tend to think of this as a graph of coolant temperature over time. As you can see, it makes this sawtooth pattern as heat is continuously added and the aquatuner turns on when the sensor temperature is reached. Therefore, the average temperature of the system is in the middle of this 14 degree range, so 7 degrees less than the sensor. Also note here that your coolant must not freeze at the lowest temperature, to ensure the sensor value is also 14 degrees or more higher than the freezing point. The final bit to add to this design is cooling for the steam turbine itself, which will overheat if we don't add this. After the point where the bypass has rejoined, we can take a pipe run and simply loop it behind the turbine, watching out for the turbine output pipe. Assuming your coolant temperature is below 100 degrees C and also not too cold, this will be simple enough, but if not, then you may need extra control. In the case that the coolant is over 100 degrees, then I would recommend adding a second cooling loop and aquatuner simply to cool the turbine, as there are a few other options. But if your coolant is extremely cold, for example in liquid oxygen and hydrogen production, then it's possible to overcool the turbine. I did once manage to freeze the oxygen atmosphere behind my turbine, which then prevented any heat transfer, so the turbine overheated. To get around this, you can add a liquid shutoff linked to a temperature sensor, and hopefully you may recognise a similar bridge which ensures the flow direction is correct. A useful tip to filling the steam room is to use two different types of water, usually normal water and either polluted or salt water. Put in the polluted or salt water first with a bottle emptier and then add a layer of normal water which will fill the space. You'll typically need to delete and rebuild one tile at the end to remove a gas bubble. There's a fairly wide range of steam densities you can use, and I would recommend anywhere between 10 to 100 kilograms per tile. Then the last point to mention for this is power, and it's fairly simple with a conductive wire feeding into the aquatuner which can be linked to the turbine as well. Note that a cooling setup like this will consume somewhat large amounts of power, to ensure your power supply is stable before building this. This is the final design for a complete cooling system in oxygen not included, and if you don't need fine temperature control, then this will work reliably as long as you keep it powered. I'm showing here my one-take visual reference for this design, which you can use as a reference for your games. The final topic for this tutorial is adding fine temperature control, and this is done with a cold injector. You can see this design here in full, which has two cooling loops, and I'll run through how this works too. The central point is to have a full cooling loop, as per the last design, which then overchills a block of diamond window tiles to a good buffer below your target temperature. Usually going below your target temperature by 40 to 50 degrees is desirable, but you may be limited by your coolant freezing point. Then, rather than using this loop directly to cool, mechanised airlocks can be automated to close and transfer the heat when they reach a chosen temperature. Because there is a vacuum when the doors are open, there's no heat transfer, so the temperature can be controlled precisely to a fraction of a degree. The doors are left unpowered and should be as conductive as possible. Because they're made from metal ores which generally have poor conductivity, using steel here will significantly help if you can spare the resource. These doors are controlled by a thermosensor in a pool of water or polluted water. With this design, the thermosensor can then be set to below the exact temperature you want to achieve. The point of having the water pool is simply to create a buffer mass of heat energy that stabilises the system. There is then a secondary cooling loop that goes around where you need to cool, which works with a bridge as already explained. And here is the one-take visual reference for this design. So that's everything for this comprehensive guide to cooling in oxygen not included. I hope this helps keep your bases cool, and thanks for watching.